Testing. Can folks in the chat hear? Can folks in the chat hear? Whoa. Okay. Here we go. All right. So, seating survey as usual, section 3 today. Upcoming deadlines today at 5 o'clock, the small group activity number 2 individual quiz, and the content video quizzes. Friday is homework number 4. Next week we will have the first exam released to you. The poll looks like it's probably, the preference was releasing it on Thursday at 5 and having it due Sunday at 5. And that is perfectly fine with me. So I will probably get it set up that way. I will confirm that hopefully today. Certainly I will confirm that by the time I do what to expect next week kinds of things. For those of you that didn't attend virtually or in person either of the last 2 class periods, I mentioned that there are a couple of Piazza posts you're going to want to look at. One of them goes into all of the details that we know so far about the exam, length of time, there's a topic list up there as well, those sorts of things. The other one is actually irrelevant now, never mind. So on that, okay. Do we have any logistical things we should talk about before we get started into content? Okay, so not very many muddiest points on the list so for today. So we will get through those and then we will take questions from the chat and from those that are here live, and we will see how things go. So the first one is somebody's talking about the colligative property vapor pressure lowering, and so saying that the student was understanding how non-volatile molecules won't vaporize, and the result of that is that it causes the evaporation rate to slow. And also the student understands that the condensation rate shouldn't be affected by this, but how does that end up resulting in the vapor pressure decreasing? So that's a good question to think about, and what it comes down to is this concept of dynamic equilibrium. And so if what we are looking at is an equilibrium where we have our sample that is a liquid in equilibrium with our sample that is a gas, equilibrium means that the amounts of on each side stay constant. They are not staying constant because the reaction has stopped. They are staying constant because the speed at which liquid is turning into gas is equal to the speed at which gas is turning into liquid. So the two cancel each other out. An analogy that somebody brought up on Piazza that I thought was actually quite good is of somebody on a treadmill. So the treadmill is going at a particular speed, and you walking on the treadmill or running on the treadmill are going at a certain speed. If you are going at a constant speed, at the same speed that the treadmill is going, but obviously the opposite direction, then your position doesn't change. If you don't change how fast you're going, but then you speed up the treadmill, then you're going to fly off the back. That changes where the position of the equilibrium is, okay? So if in this process, by having a solute in the liquid phase that slows down the vaporization process, going from liquid to gas, what happens is that we can sort of view this as that arrow getting smaller, meaning that the deposition or the condensation that's happening going the other way is still relatively fast, but it's not getting replenished by the evaporation as much. So there will be less vapor. If you have less vapor, you have a lower vapor pressure because we're applying the ideal gas law to this. So PV equals nRT. If we have less vapor, N goes down. Temperature stays the same, volume stays the same, ideal gas constant can't change, so the pressure also has to go down. So the idea here is that when you have a dynamic equilibrium and you introduce something that changes either the forward or the backward rate, then the equilibrium shifts toward the side that is now getting more. Okay. Any clarifying questions on this concept of dynamic equilibrium as it applies to vapor pressure lowering? Okay. So then there was a question with two specific examples about calculating boiling point elevation and trying to do it quantitatively with some numbers. So since we don't have many questions here, let me first start with an explanation for why having a solute in the solution changes the boiling point. The idea is that vapor pressure of any solvent as a function of temperature is determined by something you learned, I believe, last semester called the Clausius-Clapeyron equation, or maybe we actually did that this semester. I don't remember. But you can calculate the vapor pressure as a function of temperature, and you get this sort of exponential looking plot. There is going to be some some pressure that is the surrounding atmospheric pressure. If we do something like dissolve a solute into the solvent, we just showed that this will cause the vapor pressure to go down. And so what happens then, I guess I'll use green, that means that our vapor pressure is going to be lower than the pure solvent. So this is pure solvent. This is the solution where you have a solute present, and it decreases the vapor pressure. So remember that boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. Can anybody remind me of why that is, why we call that boiling? What is the point of a, yes?
So that the bubbles of gas don't collapse in on themselves?
Correct. So that when you get a bubble of gas spontaneously forming in the bulk of the liquid, the vapor pressure that is holding the bubble out has the same pressure as the external atmospheric pressure, and so the bubble won't collapse in on itself just due to that external pressure. This allows the bubble to be stable enough to then float to the top and burst, which is the phenomenon we call boiling. Okay. So if we have now done something to the solution to decrease its vapor pressure, then we have to go to a higher temperature in order to have the vapor pressure match that atmospheric pressure. So dissolving something in the solution, because doing that decreases the vapor pressure, means that the boiling point is going to go up. So if this were water, here we have 100 degrees C, and here we have something higher than 100 degrees C, maybe, 103 degrees C. And so the boiling point would be higher for something, for a solution where something is dissolved in the water. So are there any questions on this general concept of boiling point elevation before I get to the numerical calculations? Okay, so let's look at some numerical examples then. So calculate the boiling point of a 0.09 molal solution of a non-volatile solute in benzene. We have the boiling point of benzene at the atmospheric pressure we're dealing with, and we have a boiling point elevation constant. Okay, so the equation is very simple for this. Our change in boiling point is equal to the concentration of the sample in molality times the boiling point elevation constant. So in this case, we have 0.090 molal. We have 2.53 degrees C per molal. Notice that the molals cancel and we're left with degrees C. You multiply this, I will get a calculator, 0.09 times 2.53 gives us 0.2277 degrees C. Now this is a change in boiling point. So we started at 80.1 degrees C. So our new boiling point for the solution, I can't spell apparently, is going to be the 80.1 plus the 0.2277. So since we only have one place after the decimal here, this is going to be 80.3 degrees C that you have. Okay. Any questions on that general approach? Okay, yes?
So what does that M stand for again in this equation?
What is the M? The M in that equation is the concentration in units of molality. Okay. Does anybody remember what the units of molality mean? Yes.
Mole solvent over kilogram solvent, or mole solute over kilogram solvent.
Correct. Moles solute over kilograms solvent. Okay. So in most of chemistry, we use molarity because that gives us a very convenient way to take a volume of our solution and figure out how much of the reactant, the solute, we have. In this case, for some technical reasons that you won't get into until, say, a physical chemistry class, molality, this more unusual unit of concentration, is a more natural unit to use for freezing point depression and boiling point elevation. It is not worth the really long sidebar we would have to go into as to why we are using molality instead of molarity. So just, I'm asking you to take my word for the fact that this is pretty much the only place you're going to need to use it. Okay, all right. Okay, so the second question is nearly identical to this one in concept, except you haven't, we aren't given the concentration, we are given enough information to find the concentration. So we have 1.0 grams of glycerin with a known molecular formula in a given mass of water. So this becomes essentially a dimensional analysis problem. We have 1.0 grams of glycerin, C3H5OH3, and we need amount of glycerin, the solute, over amount of solvent, which in this case is 47.8 grams of water. Now I'm going to point out here something I've been pointing out for several class sessions now, which is when I'm writing units, I am not just putting grams over grams. It is grams of this and grams of this. That is because we need to be able to independently convert. You know, in this case, it's going to be converting to moles, right? And writing the entire units, which includes the substance, prevents all sorts of mistakes. So we are trying to get into units of moles per kilogram. So we need to convert grams of this to moles of that. So grams of C3H5OH3 to moles of C3H5OH3. Oh, that goes outside. And so we simply use the molecular weight or the molar mass of this compound. So you can do it very accurately by taking the full atomic masses of each one. I'm going to, for expediency's sake, use rounded values. Carbons are about 12, hydrogens are about 1, and oxygens are about 16. So we have 3 times 12 is 36. The oxygens, we've got 3 of those, so 16, 32, 48. And hydrogens, we have 5, 6, 7, 8. So 16, 4, 5, 6, 7, 8. Looks like 92 grams per mole. Assuming I did my arithmetic right, which I wouldn't count on. I can take integrals and derivatives all the time. Arithmetic sometimes gives me problems. So we now have grams of solute canceling, and we now have moles of solute in the numerator, which is what we wanted. But we need kilograms of water in the denominator rather than grams of water in the denominator. So we need to multiply by something that is going to go from grams of water to kilograms of water. What's our relationship there? Straight just from the SI prefixes. What does kilo mean? 1,000. So there are 1,000 grams in 1 kilogram. There aren't many things that I recommend people memorize, but the main SI prefixes are a very good thing to memorize, knowing what a centa means, or a milla, or a killa. Those are the main ones. Those 3 are the ones you're going to use over and over and over again. Depending on what field you go into, you might need micro, nano, or pico. But the milla and killa and centa, you definitely should know. Okay, so grams of water cancel, and we now are going to end up, I have that backwards, don't I? They don't cancel. I have grams of water times grams of water in the denominator and kilograms in the numerator. So this instead should be 1,000 grams of water over 1 kilogram of water. And so now this correctly cancels with the numerator, and we are left with moles of solute over kilograms of solvent. Okay. I'm going to assume you can plug that into a calculator and get the value. And that becomes your concentration in molality. And then you just use exactly the same equation. It gets plugged in here. Because we're dealing with a different substance, you have a different boiling point elevation constant that you plug in here. You just multiply them together, you get your change in boiling point. And that change in boiling point then gets added to the original pure substance boiling point to get your final value. So conceptually, these two problems are no different from each other. It's just that you have to actually determine what the concentration is in the second case. Okay. Any questions on this type of calculation? Yes?
Is this similar to like what a test question would be like?
So this might be part of a test question, but it wouldn't probably be an entire test question. So generally what I would do is try to put this into a sort of a larger context. And so you're having to do this kind of calculation as part of interpreting some kind of phenomenon that's going on. So one of the things I'm thinking, so let's talk about, say, because I haven't thought as much about the colligative properties questions yet on the exam as I have some of the others. But so for example, when talking about phase transitions or something, and interpreting phase diagrams, maybe doing cooling curves and those sorts of things, I'm thinking about trying to put those questions in the context of planetary atmospheres on other planets in the solar system. And so instead of dealing with one atmosphere pressure, you're dealing with something that on Mars is like 1,000th of an atmosphere of pressure. And so that's going to put you into a completely different location on the phase diagram, but you would then be interpreting what's going on in that system based on those conditions rather than the terrestrial conditions. So that's the kind of thing that I'm thinking about. So these kinds of calculations would be part of an exam problem, but probably would not be the entirety of it. Okay, so that gets us through the very short list of muddiest points that we had listed. I am happy to open things up to other types of questions from anybody. What would people like to talk about? Yes?
Can you make room for yourself having a hard time understanding the calculations for like the 10C and whatnot? Could you do like an example using?
Okay, so I do want to point out that, so that the question was about trying to understand the 10C and like the 5X kinds of notations in the homeopathy activity. I do want to point out that the purpose of those concentration measurements was to point out to you how in this particular industry, in the homeopathic industry, they don't use standard chemistry notation for things. And so what we were trying to do with that activity was, let's see what happens if we take what they're doing and put it into standard chemistry notation so that we can then see, are their claims making any sense at all? And the outcome of that was, no, they really don't, because you end up with, in order to get even one atom of the active ingredient, you need a volume of water that would make this giant cylinder that would extend past the orbit of Saturn. And so any dose you buy off the shelf will have 0 active ingredient in it. Literally, 0 active ingredient in it. So coming out from that activity, am I going to be testing you on being able to do homeopathic dilutions and use the C scale and the X scale? No, because that's not the purpose of the activity. I don't care in the long run if you take away from it, yes, I can do homeopathic remedies and now I'll open up my own shop and sell homeopathic remedies. The idea of it was to go into it to understand it enough that you could then translate it into a more meaningful concentration unit of molarity and then figure out what it would mean in that context. So I'm happy to go through that if you want me to go through the C scale and the X scale and stuff so that you understand the activity a little better. But I will not be asking you exam questions on the C scale or the X scale or something, because from a chemist's perspective, they're stupid scales. Does that make sense? Okay, so do you want me to go into that a little more? So.
I'm just confused on like how to calculate. So like for instance, one of the questions is what is the concentration of a 10C low potency dilution of pure arsenic trioxide?
Okay. Sure. Okay. So the idea is that in the earlier questions that led up to that question, there should be a pattern that you start to see. Okay, so if I'm remembering correctly, the concentration, if we pretend that the that the starting pure sample of arsenic trioxide can be measured in concentration. It's something like 18 molar or something. Is that what most people got? Okay, I'm going by memory here. So if that's what we're starting with, something that is 18 molar, if you do a 1C dilution, what that means is you take 1 milliliter of this and you dilute it to 100 milliliters, okay? So what that does to the concentration is it takes the decimal point and moves it 2 spaces to the left. So 0.18 molar is our 1C dilution. If you do a 2C dilution, it moves it 2 more points to the left. If you do a 3C dilution, it moves 2 more points to the left. Now let's write this in scientific notation, because when we get up to something like 20C, that's going to be easier to deal with. So this is 1.8 times 10 to the negative 1 molar. This is 1.8 times 10 to the negative 3 molar. This is 1.8 times 10 to the negative 5 molar. So what's the pattern that we see? What is 4C going to be? 1.8 times 10 to the what? Negative 7 molar, right. So what is 20C going to be? Well, so 7's at 4, 9, 11, 13, 15, 17, 19, we're up to 10C. And then we're going to be adding 2 times 10 again to that. So this is then going to become negative 39. So 1.8 times 10 to the negative 39 molar.
Oh, they can't see the paper.
Oh, thank you. Can you see it now? Oh, ha, ha, ha. Yes, thank you. I had changed it to point at me instead of this screen. There we go. I apologize to the chat. Yes, so for the chat, what we were doing was saying, it starts at 18 molar, 1C moves the decimal place over by 2 to become 0.18 molar. 2C moves it over 2 more, 0.0018 molar, and so on. And if we write it in scientific notation here, we have 1.8 times 10 to the minus 1, and each step we're going down by a factor of 100, or increasing the exponent by a factor of negative 2. So that means at the 20C, we have 1.8 times 10 to the negative 39 molar. Okay, yes?
Does equation or a calculation we could do if we didn't want to count, like, say, all the way up to the 200C?
Well, so let's see what the pattern is. 1 becomes 1, 2 becomes 3, 3 becomes 5. So we know that whatever our C value, so if it's XC, then it's going to be 2x minus 1. Okay? And that's not something you should, memorize. That's just looking at what the pattern is. You know it's going up by 2, so the x has to be multiplied by 2. Well, if I take 2x, what do I have to do to get to minus 1? I have to subtract 1 from it. And then you check yourself on a couple others, and it still works. Okay? So that should be something you can look at the pattern and then extract an equation from. So for the 200C then, this is going to be 1.8 times 10 to the negative 399 molar. All right? Okay. Was there somewhere further down this path you wanted me to go with it? Yes.
Can you show us how to calculate how many ions, like,
Sure. So let's look at the 20C version right here. Okay. 1.8 times 10 to the negative 39 molar. Moles per liter, and let's be specific, moles of what over liters of what? Solute over solution. So this molar means moles solute over liters solution. And I give you the hint in the question that if you take the inverse of this, you can work towards getting the volume of that will be required to have one atom or one molecule of the solute in it. Let's look at why that's the case. If we take the inverse of this, we are taking the denominator, liters of solution, over 1.8 times 10 to the negative 39 moles of solute. So if we take 1 over 1.8 times 10 to the negative 39, let me get my calculator out to do that. 1.8 E39, change sign, and I do 1 over that, we get 5.5 times 10 to the 38th in units of liters per mole. So that is how many liters of solution you need to get 1 mole of solute. Well, we don't care about we're not trying to get a mole of solute, we're trying to get 1 atom of the solute. How do you go from moles to atoms? Yes, Avogadro's number. So 5.5 times 10 to the 38th liters solution over moles of solute times, and we need to figure out, does Avogadro's number go in the numerator or the denominator? So what we want is we want moles over atoms. And so that means that we want Avogadro's number in the denominator because it's 6.6 times 10 to the 23rd atoms per mole. 6.6 times 10 to the 23rd atoms per 1 mole. So we now have moles of solute canceling with moles of solute. Let's do that calculation. So we have that divided by, this isn't 6.06. I just had a brain fart on Avogadro's number. 6.02, yes. Man, I was giving you, I think Planck's constant is what I was putting in here. I apologize. 6.022 times 10 to the 23rd. Okay. 2 times 10 to the 23rd. And we get, I'll show it right there. We'll call this 9.2 times 10 to the 3, 6, 9, 12, 13, 14 liters per atom. And so just think about those units. This is saying that you need 9 times 10 to the 14th liters of your solution in order to have 1 atom in it. Okay. This is the quantity that I was saying you need to, we don't have a mental picture big enough to do this. And so what I was having you do in the activity was to picture the sun in the center, picture the Earth out here in orbit. Boy, that's, okay, the sun's a little closer to the center than that. Now picture making a cylinder that is the width of the Earth. And we're going to make this entire cylinder that covers the entire solar system from the sun going out, with the width of the Earth going out as far as possible. And how far out does that cylinder go to have this volume? What was the planet that whose orbit it entirely encompassed? Saturn. That's right. You do this calculation and you find that in order for a 20C homeopathic remedy to have 1 atom of active ingredient in it, you would need to have a sample of this remedy that's as thick as the entire diameter of the Earth, that is centered on the sun and extends out past Saturn to have 1 atom. This is what's going on when you have successive dilutions. You're diluting it to the point where there is no active ingredient left. So I said in my sort of intro video to this entire class that one of these activities you're going to be doing is going to use some basic chemistry concepts to prove that an entire $14 billion per year industry is a fraud. Homeopathic remedies are a fraud. And you can prove it using general chemistry. Yes?
So the question asks how many ions of arsenic are present.
Yes.
My group, we did 2 ions with arsenic trioxide.
Okay, so the idea here is that when you're first determining the initial concentration, what we're really kind of caring about at that point is the concentration of arsenic ions at that point. And so the way I would do that is to, at this point, have, we have the moles of As2O3, but then we convert that with 1 mole of As2O3 to 2 moles of As3 plus ions at that point, okay?
So would that change your last answer?
So it's an interesting question. I'd have to go back to my key and make sure. Did I do this correctly at this point in the 18, or should it have been 36 at this point if this were done?
No, I think that was just asking for the molarity of the solution, and it doesn't start asking specifically about arsenic.
Okay. So the answer is at some point you have to do that.
Yeah.
the question then is where do you do it? And so when this is graded, when the quiz is graded, I'm going to go back in and double check and make sure that it's going to, it'll account for it, it'll grade it correctly as long as you do it somewhere, but it doesn't matter which step you do it at. Okay, so I'll make sure I get that figured out. You bet. But you know, the ultimate conclusion that we're drawing about, you know, where is this a reasonable way to make a remedy for something is not going to be changed by a factor of 2. So that the ultimate point is not going to change. Okay. Anything else on this? Okay, let's, any other topics we can talk about? We've, most of this week's material is on the colligative properties stuff, and we've only had a couple of questions about that. We talked a bit about the vapor pressure depression. We went through some calculations for the boiling point elevation. Freezing point depression is essentially, from a calculation standpoint, identical to boiling point elevation. You just have a different constant, and you need to be aware that it's going down instead of going up, so that the delta T that you get is going to be causing the freezing point to go lower. The way to remember which direction those things go is thinking about a phase diagram. You've got the liquid region on the phase diagram, and you're expanding the liquid. With both, so the boiling point goes up and the freezing point goes down. Okay, I probably was doing those from my perspective rather than from your perspective. The oddball out is osmotic pressure, and sometimes it's a little hard for people to wrap their brain around what osmotic pressure is. So I could certainly, if people are confused at all about that, I could go into that. But if everybody managed to get it, I don't have to. Just throwing out some ideas.
They said, someone on chat said yes about the osmotic pressure.
Okay, so osmotic pressure. Here is the idea. Imagine you have a membrane, so a semi-permeable membrane. Semi-permeable meaning that solvent molecules, which, I wanted my blue pen and it's gone. Oh, well, okay, so we'll make green solvent. We've got solvent molecules floating around, and the solvent molecules can pass through, but we have solute particles that cannot. Okay, and the effect that this kind of setup has on the flow rates is similar to the effect that solute particles have on vapor pressure, on evaporating, because what we have is an equilibrium that is going on where we have flow in this direction and we have flow in this direction. And if there were no solute molecules, then those two flow rates would be equivalent. So if you set this up, and typically what we will do to make this kind of measurement is we will use a U-tube, place the semi-permeable membrane here, and we will put solvent on both sides. And so if the flow is equal in the two directions, then the two heights stay the same in this kind of system. Now, imagine what it would be like if there were no semi-permeable membrane here. Gravity pulling on the two sides will cause the two heights of, to be equal. So if you start with more on one side than the other, then there's a greater gravitational force pulling down on the side where there's more, and it will pull it down until it's equal, until the pressure, until the forces are equalized on the two sides. Putting the semi-permeable membrane in place doesn't change that. But then if you put solute on one side, so in this case, very similar to how solute molecules in a solvent will prevent the evaporation of some solvent molecules, the solute molecules on this side prevent the flow of some of the molecules to the left. But it doesn't prevent the flow of molecules from the right. So this gets smaller, which means that the flow to the right is greater than the flow to the left. And so there ends up being a larger force or a larger pressure this direction. And so the system will transition into something that looks like that. And so we have, when there is a net force, there is motion in the direction of the net force. A pressure is a force per unit surface area. And so what we are feeling across this membrane due to the difference in flow rates is known as osmotic pressure. And when we are now in this situation, we also have this height difference. And so this side from the force of gravity is feeling an extra pressure due to the weight of this extra water that's on this side. So when the osmotic pressure equals the extra pressure due to the extra weight of the water on this side, then you have reached a new equilibrium. And so the flow will then be equalized because this pressure equals that pressure, and so all of the flow rates are now equal. Okay, so this osmotic pressure that we feel has an equation. It is denoted by the capital Greek letter pi, and it equals the concentration in molarity. So this is the one colligative property where molarity is the natural unit. So the concentration in molarity times the temperature, I believe, times the ideal gas constant. I'm doing that from memory. I'm hoping I did that correctly. These are the kinds of equations that if I were having to do it myself, I would look it up. So I'm going to write here, double check. So that is what osmotic pressure is. And this is how you calculate the magnitude of that osmotic pressure. Now notice something that's happening as this occurs. With pure solvent flowing this direction, what happens to the concentration in this side? It decreases. This is actually diluting the concentrated sample. And so in your calculations, you may have to take that into account. You may have to say, okay, well, I'm starting with this, this pressure but that I'm calculating, but once it comes out and equalizes, I'm getting a lower pressure because it's now been diluted. And the way to think about the direction, so it's common to sort of forget, okay, I've got a semi-permeable membrane, which direction is the flow going to be? Which direction is the pressure going to go? The way to remember that, in my mind, is that the pressure is pointing in the direction that will try to equalize the concentrations. So if this is concentrated and this is dilute, then the flow is going to go in the direction where it's going to dilute the concentrated one. Does that make some sense? Okay. This is a very important colligative property for technological reasons and for biological reasons. For technological reasons, a lot of water purification techniques are done by reverse osmosis, which is where you have this, so you've got impure water over here, maybe even seawater. You have a semi-permeable membrane in place, and you apply an extra pressure on this side. You hook up a really strong pump to push the water through, and you end up getting pure water out on the other side. That's really hard to do. The amount of pressure you have to apply is huge, so you end up with having extreme, this is a very energy-intensive method for purifying water. But if you need to purify water, you need to purify water. The military does this all the time when they have tanks out, trucks out that are specifically designed to do this. If you go camping and have one of those water purification things that you pump by hand, and you may notice, boy, I really have to push on this thing. This is what's going on. You are having to overcome the osmotic pressure that is pushing back against you due to the difference in concentration on the two sides. In order to get pure water out, you are now having to push against the osmotic pressure to get flow going the other direction. And then in biology, cell membranes, the surfaces of alveoli, there are semi-permeable membranes. The stomach lining is a semi-permeable membrane. And so understanding how osmosis works and how fluid will transport across those membranes is important to understanding how biology ends up working. The example I use in the video is if you inject a medicine into somebody's vein with where the salt concentration is not high enough, well, there's going to be water flow across the cell membranes from what you injected into the blood cells. The blood cells are going to expand and burst. If you have too high a concentration of salt in what you inject into the bloodstream, then the osmotic pressure is going to be the other direction, and the cells are going to extrude their water and shrivel and die as a result. So it's very important that injected medicines be isotonic, meaning they have the same salt concentration as the cytoplasm of the cells themselves. So those are some areas where this application is extremely important. Okay, we have about 11, 12 minutes left. Is there anything anybody else would like to talk about? Everybody's feeling comfortable with this material, I guess. Okay, well, I guess we can call it early today. Thank you all. There's some good questions and some good discussion. I appreciate it. Oh, one quick thing. So I posted about this on Piazza, but one of the things that I did yesterday in class was I tried to tackle the issue of identifying intermolecular forces from a different direction from what I've done before, because I was still getting some Piazza questions about that, and so it seems to be a persistent kind of confusion. And so I have created a new menu on Blackboard for resources. And one of the things on there is a short PowerPoint that you can download that has some tables in it and a procedure you can follow with those tables to identify what intermolecular forces are present. So it's got, you know, rows and columns, rows for one molecule that's involved in the intermolecular forces, columns for the other molecule, and you identify, okay, this one's an ion, so I leave that row. It doesn't have a dipole, so I mark out the dipole row. And then similar things, hydrogen bond acceptors, hydrogen bond donors, and so on. And then the things that are left are the intermolecular forces that you have. In addition to that, a lot of people, I've been a little surprised at how persistent some confusion about looking at a compound and saying, is that an ion or not, have been. And so I spent some time on that question in yesterday's class. That class video is up now on YouTube. I've linked to it, and in the timestamp listing for it, I specifically call out a discussion of identifying ions as a discussion that we went into in detail yesterday. So if you have been having that question, that's a great thing to go look at. Thank you.